Say we have the compound sodium or silver nitrate, and so that is being put into some water. So let's say we have a solution here of silver nitrate, and then we have another solution of sodium chloride. All right, so we're going to put these two solutions together. So in this solution, the silver nitrate is soluble, it's dissolved. The sodium chloride also is soluble, it's dissolved in the water. So we have Na ions and Cl ions floating around. We have silver ions and nitrate ions floating around. These two get added together. The question is, what's going to happen now? Do we continue to have silver and nitrate and sodium and chlorine ions floating around, or perhaps could a reaction happen? Now, although silver and nitrate together are soluble in water, and sodium and chlorine are soluble in water as ions, when the two are added together, new combinations can form. So now the silver can combine with the chlorine, and the sodium can combine with the nitrate, which leads to the possibility that maybe one of those combinations is no longer soluble. It no longer is able to be dissolved in water. And in this case, the silver and the chlorine, that combination, it turns out, is insoluble. So it forms a solid that would precipitate down to the bottom, while the nitrate and the sodium continue to float around. So this is the idea of a net ionic equation. When we have the combination of substances that are in solution and two different substances, now some of those substances may form a precipitate or come out of solution, and when that happens, that leads to an overall or net change. So that's where we have the idea of a net ionic equation. So we could rewrite this equation, for instance, like this, where we have all the ions shown. The ions for silver nitrate are shown here, and the ions for sodium chloride are shown there. So we're showing them separated or dissociated, and the product is solid silver chloride and sodium and nitrate ions still floating around. So if we cut out the things that didn't change, which would be the nitrate is on the same, did not change between the reactant and the product side, and the sodium didn't change, reactant and the product side. What are we left with? We're left with what we call the net ionic equation, which is the net change. Things that didn't change, these are close. They were floating around before, and they're around in the water. So that's net ionic equation. This reaction would plus binds with chloride to make silver chloride solid. So Ag, silver, plus chloride combines to make silver chloride. So let's look at a few examples of solving net ionic equation problems. So our first one is silver nitrate again, and that's aqueous, combines with potassium sulfide. So our first step in figuring out the net ionic equation is we need to write the dissociated equation showing how these ions separate. Kind of this equation. Since these are aqueous, we know that they're going to separate out into their ions. We have ionic compounds, of course, in each of these, so we'll need to review what charges each form. Silver forms a 1+ charge. That's a known. We might need to just memorize that forms a 1+ charge. So we know that we have silver +1, and we'll write aqueous since it's dissolved in water. The nitrate, polyatomic, so we have to remember this is it's polyatomic and it's a -1 charge. That. So NO3, negative, also aqueous, dissolved in water. Then we have, so here's our first set. So that's the silver and the nitrate, silver nitrate, shown dissociated into its ions. Then we have the potassium, and potassium follows the pattern of everything here in group 1A, that it forms a 1+. So we'll write K plus aqueous, and then the sulfide follows the pattern. Group 6A compounds form a -2 charge. They want 2 more valence electrons to get an octet. Going to be S2- aqueous. So now that we have the dissociated form, and of course this refers to the potassium sulfide, these last two there, now we can go about figuring out if anything in this combination might be insoluble, or there might be something that changes more generally. So if we look at the various combinations that can occur, these two are already together, so we don't really need to compare them. The silver and the nitrate, those are already together. We know that that combination is soluble. It's aqueous in water. These two, of course, were already together as well. The potassium and the sulfide were already together. We know that that combination is aqueous. But now that these are mixed together, we have new combinations that can occur. We have the combination of the nitrate with the potassium, and we also have the combination of the silver with the sulfide. So we need to look at these new combinations and see if those might be soluble or insoluble. So the potassium and the nitrate. Now, solubility rules come into play here. So we might need to look up these solubility rules. Typically, group 1A compounds are soluble, and we can see this table here from our textbook. Now, notice that potassium is on the soluble side, and nitrate is also on the soluble side. So we can predict from that, since both of those are soluble, that the combination of potassium and nitrate would still be soluble. So let's go ahead and write those out as ions. So we have potassium. My arrow here, I'm going down below because I'm out of space, so I'm going to write potassium here as a product. And the nitrate, NO3 minus. Okay, so those are soluble, and so nothing is changing. They are still in their ion forms as they are dissolved in the water. Now, let's look at this other combination here, the combination of the silver and the sulfide. So the silver is shown right here on the insoluble chart, and the sulfide is right there under insoluble as well. So we can predict that the combination of silver and sulfide would be insoluble, or it would form a solid when those two ions are combined. So we can then write the silver and the sulfide together. Now, we're going to have to do a little figuring out here though. So we know that in this space right here, we're going to be combining the silver and the sulfide. Now, this forms a new compound that we're then going to have to figure what the formula would be. So the silver and the sulfide, those two, we can use the crisscross method to formula that compound. And so if your lessons, crisscross method involves a way of neutralizing the ionic compound. I'm taking this 2 here, 2 silvers with a 1+ charge to neutralize the 1 sulfur with a 2- charge. And so as doing that, I need the 1, and I put that as a subscript there. So it's Ag2S. So we have, as this compound, silver sulfide would be Ag2S, and in parentheses, solid, since it does form a precipitate. So right now, we've completed the Ionic equation. We need to take a look and see if there are any spectator ions, anything that does not change. Well, we see that potassium didn't change. It's here on the reactant side and on the product side. So that's a spectator. We see that nitrate did not change. It's on the reactant side and on the product side. So that is a spectator ion. Write the net ionic equation. The net ionic equation, we're going to write everything except for the spectator ions. So what's left is silver, Ag+, combines with sulfide, S2-, to silver, Ag2S solid. Now, I forgot to mention here is when we had to form this new compound, we have the necessity of rebalancing the equation. So notice that silver here, we have 2 on this side. So we would need to put a 2 coefficient there to balance the equation. The sulfide, there's still 1. And so we also would need a 2 here to balance this net ionic equation. So we have 2 silver ions plus a sulfide makes Ag2S. Okay. So there's a lot to remember, pulls together a lot of information we've done all throughout the year. Let's go ahead and take a look at a second example. So this next one we have ammonium chloride combining with sodium sulfate. All right, so let's start again by writing the complete ionic equation. So I guess we can label these things here. So we have the net ionic in the last problem. This right here is the complete ionic equation. So we're going to write this thing for this next problem. So the complete ionic equation, we're going to show the ions that these separate into. Now NH4 is the polyatomic ion ammonium, and we have to remember that that is +1. So we have NH4 plus 1, and that's aqueous. And then we have chloride, that forms a -1 charge. We have sodium, which forms a +1 charge. We'll put the 2 coefficient in front, and A+, AQ. And then we have the sulfate here. And so that is polyatomic, once again, SO4, and it's a 2- charge. All right, so look at the combinations that can occur. We have the chlorine that can combine with the sodium, and we have the ammonium that now can combine with the sulfate. Of course, these two, again, were already together, as we can observe from the last problem. These were together here as ammonium chloride. We already know those are soluble. And of course, these were together as sodium sulfate, so we already know those are soluble. So we're looking at the new combinations. So sodium chloride, we can start with that. So this is good old table salt. Sodium's right there, chloride's right there, and of course table salt is soluble. So we know that these two are soluble. I'll write my arrow here. So we have Na plus, or 2Na plus, and Cl minus Aq. Okay, so nothing's changing there. Then we have the ammonium and the sulfate, this combination. So ammonium's right here, sulfate's right here. Those are both on the soluble side as well. So nothing changes there. So we still have ammonium, NH4 plus, still in the ion form, still dissociated, and SO4, 2 minus. Well, did anything change? No, nothing changed. We mixed these two solutions together. They were dissociated into their ions, and they are still dissociated into their ions. Nothing changed. So there is no net ionic equation to write in this case. There is no change. It continues to remain that we have ions dissolved in the solution. Go on to the next problem. Take a look at NH aqueous combining with H2SO4 aqueous. So we have sodium hydroxide and sulfuric acid combining. So split this up into its ions. We'll write the complete ionic equation. So we have sodium. Sodium forms a +1 charge. Hydroxide is polyatomic, OH minus. Then we have over here hydrogen, which is H plus, and we have 2 of those. And we have a sulfate. Okay, so again, we're looking at the new combinations. We know that these two were together already. The sodium and the hydroxide, those are aqueous, and we know that the hydrogen and the sulfate were together already, so those two are aqueous, of course, together. But now we have new combinations, the side and the hydrogen, and the sodium and the sulfate. So let's take a look at sodium and sulfate first. So we have sodium and we have sulfate. And so those are both on the soluble side of this table. So we can predict sodium will remain as an ion, and sulfate as well will continue to be dissolved or aqueous. Now, hydrogen and hydroxide. what do those make when those go together? Well, this is a little different. We don't so much have something insoluble in this case, but rather hydrogen, two hydrogens and an oxygen make water. And water is what forms the solvent here. So we don't consider that to be part of the solute. We put here liquid. And so water does in fact come out of solution. So water, in this case, is the change. It produces water. So our net ionic equation, just like we did before, we can see that sodium change, that gets taken out. That's a spectator ion. The sulfate has no change. That comes out. That's a spectator ion. But we do have a change with the water. So we can rebalance this equation here. In our net ionic equation, we'll actually need to take out this 2 coefficient for the hydrogen. And we have this, an OH hydroxide combines with 1 hydrogen ion to make H2O liquid. And there we go. We have our net ionic equation showing this reaction.